Thank you for joining my conference talk. In this presentation, I'll be covering the design of an integrated power supply unit for textile-based wearables. I'll talk about how we integrate a flexible RF energy harvester, a Rectenna, with a textile-based supercapacitor spray-coated in standard fabrics, and we'll discuss how I present an end-to-end solution for powering wearable, flexible, and printed electronics. So, what energy sources are there for printed and flexible electronics, or more generally, wearable electronics? Batteries are bulky and not sustainable, and the more sustainable option, the lower cost option, and the more environmentally friendly option is really energy harvesting, where you don't have to dispose and charge batteries. Energy harvesting could be from ambient sources, solar power, light, thermal gradient, or even harvesting vibration. But the problem with these ambient sources is that the energy is highly dependent on the environment where your wearable device is deployed. The other problem is wearable and printed electronics are normally two-dimensional. They are planar structures, usually thin and flexible. And to realize high efficiency, for example, vibrational energy harvesting, you may need complex 3D structures for certain high efficiency resonators. On the other hand, wireless power transfer radio frequency energy harvesting can be thought of as a semi or quasi-ambient energy source, where the power could be existing in the environment, but we do have more control on how is the power delivered, where is it generated, and how it propagates to the user. The other main advantage of RF energy harvesting in wearable applications is that very high efficiency antennas could be realized using flexible and printable materials on wearable substrates such as standard E-textiles. And in terms of electronic components, we're only talking about packaged Schottky diodes, which could be protected and encapsulated for more reliable wearable operation. Now, as we have covered the motivation on why we use RF energy harvesting for wearable electronics and for e-textiles, we need to think of what a wearable RF energy harvesting power supply needs to contain. The main component is the power generation. We need some method of creating the DC power and harvesting the RF radiation. And then normally, because RF energy results in microwatts of DC power, which are not enough for most low power applications, we still need energy storage. In this case, this is best achieved using a supercapacitor. So we need to integrate a supercapacitor in textiles with a rectifying antenna or a rectenna for harvesting the RF energy. In the figure on the left-hand side, you can see a diagram of our proposed device, where we have a flexible rectenna as well as spray-coated capacitors integrated in the same fabric. And the prototype in the photograph shows the rectenna directly connected to the capacitor cells, which stores the DC power, can keep it as energy, and then allow it to discharge into the load. For a very brief background, RF energy harvesting using rectifying antennas is about harvesting the voltage peaks of a high-frequency electromagnetic plane wave, which could simply be signals scattered from wireless communication, receiving it and converting it using Schottky diodes or other rectifiers into DC power. The main requirement for this to happen is one, we need to have an antenna to receive the power. This antenna needs to have radiation patterns which match the incident wave. For example, if it's a directional antenna, that antenna needs to be looking where the wave is coming from. The other requirement is polarization, how the electromagnetic fields move and how we need to align the antenna's polarization or have a mechanism to harvest all polarizations, such as using dual polarization harvesting to recover any randomly polarized wave. This is only enough to capture the wave, but not enough to convert it into DC power. The second half is the rectifier. Rectifiers are normally made out of Schottky diodes, and they are highly nonlinear devices where the impedance varies with frequency, power level, and DC load. So we really need to match the input impedance of the antenna to the rectifier to ensure maximum power transfer between the energy harvester and the energy converter, and therefore get high efficiency power transfer to our resistive DC load. Otherwise, our power will be reflected back to air and we'd not get any harvesting. In order to design a high-efficiency rectenna, we use antenna rectifier co-design. Antennas are normally designed with a real impedance that could be 50 or 75 ohms depending on the application, and then a matching network could be used to transform this 50 ohms into the impedance of the diode for the operation conditions of the rectenna. In our way, we avoid this by designing the antenna to directly match the antenna of the rectifier. So it's directly match the impedance of the rectifier. We model the antenna as a power source with a certain frequency, and then the power source has got its own characteristic impedance, which is a complex number, and we tune this complex number along with while simulating the circuit of the rectifier to maximize the power delivered to our resistive load. On the right hand side, you can see the layout of the rectifier we're using in this work, which is a simple voltage doubler, and we have the input port with a complex impedance, which is the antenna we'll be designing. This rectifier is optimized for a low-cost, flexible polyamide substrate, which we fabricate using photolithography. In order to fabricate our rectenna, or more generally any RF circuit filament for flexible wearable applications, we use standard photolithography. An RF filament fabrication is fundamentally no different to any flexible PCB. The base or substrate is an ultra-thin polyamide Kapton copper laminate, commercially available. Kapton is brand name, and then we etch it using a standard photolithography. Photoresistive ink is deposited onto the substrate. You could spin coat it, print it, roll coat it, virtually any method to deposit a uniform layer of photoresist. And then we use UV light to transfer the pattern onto the photoresist using a printed dark film mask. Finally, once the photoresist is cured, we etch away the excess copper to get our final traces in an etching tank. As a result, we have a simple and straightforward method of fabricating high conductivity, flexible and lightweight RF coplanar structures typically in 2D circuits. Once the thin flexible circuit filament is fabricated, the components can then be either mounted manually or using a pick and place machine. A key advantage of this approach over printing conductive inks on fabrics or on polyamides is withstanding higher temperatures. Polyamide has excellent thermal properties, and it's the same with epoxy and copper sheets, which allows us to use conventional soldering methods to mount the components, which in this case are our Schottky diodes. Once the components are mounted, they are not entirely protected. They would not withstand the harsh use of wearable electronics. They can peel off or crack under bending, so we use encapsulation to improve the mechanical durability. In this case, we use an ultraviolet curable epoxy globe-top encapsulation to protect the diodes from bending and to give them more mechanical reliability. And finally, the textile aspect comes in. Because this circuit is very thin and long, it could be woven or integrated into standard textile weaves, which is a process we have presented in multiple experiments and for multiple applications. In this slide, you can see the fabricated prototypes we have used. In the left-hand side, you can see the flexible rectenna on a very thin polyamide substrate, and you can also see the rectifier in a compact area entirely covered with a globe-top epoxy. And in the right-hand side, you can see how it could be inserted into a bespoke pocket into any textile weave for improving its mechanical durability and for making it more user-friendly and more aesthetically pleasing. Now we move on to how our rectenna performs. The main figure of merit in a rectenna is the power conversion efficiency. The power conversion efficiency is defined as the ratio of the DC power delivered to the load compared to the incident RF power available from the antenna. RF power levels in typical RF energy harvesting applications are in order of milliwatts or below 0 dBms. And we use in our rectenna a diode from Infineon, which has a low threshold voltage but also a high breakdown voltage. This allows us to rectify both very low power levels down to 10 microwatts in this graph, as well as relatively high power levels with very high efficiencies. And as you can see in the primary axis of the figure, our rectenna achieves an efficiency exceeding 90% above 0 dBms. The DC output voltage of the Rectenna is also pretty high, so the maximum voltage exceeds 8.5 volts. This allows us to really charge the supercapacitor rapidly and improve the voltage of the supercapacitor in smaller charging times. Talking about the energy storage in our work is a textile-based spray-coated supercapacitor fabricated on a standard cotton fabric. And because we use spray coating of the electrolyte as well as printing of the electrodes or connecting using conductive fabrics, this could be transferred to virtually any wearable fabric. The double-layer all-textile supercapacitor has a very high charge density, and in a single cell we have a capacitance of 7.1 millifarads. In order to improve the voltage rating of the capacitor and to allow it to withstand the voltage output of the Rectenna, we connect three capacitor cells in series, and then we characterize the device using electrical impedance spectroscopy to come up with the equivalent circuit model. We come up with a standard 4-branch equivalent circuit models with the RC equivalent circuit of the capacitor, and this agrees with the measured results within 1%, so there's no need for adding more branches to the circuit model. Now, testing our integrated device, we use a signal generator of known RF power levels to characterize our device as a first step. The advantage of this approach is that we know exactly how much RF power is available at the device. We are not affected by additional wireless testing uncertainties like multipath effects or non-line of sight effects. And we measure the voltage across the capacitor up to 5 RC time constants. And we can see that from power levels as low as 1 milliwatt, we can easily charge the capacitors to 1 volt in under 20 seconds, meaning that this capacitor and this Rectenna could be easily used to power real-life, low-power Internet of Things, wearable Internet of Things. The next step is the integrated device test using the wireless power provided by the Rectenna to charge the capacitor. So we implement the test setup. You can see in the picture we use a commercial transmitter, a Powercast, operating at 915 MHz, license-free band of wireless power transfer. And the transmitter transmits 3 watts of power. The distance between the transmitter and the receiver is 1.2 meters, and the Rectenna's output is directly connected to a supercapacitor without any intermediate power management circuitry. And finally, an oscilloscope is used to measure the DC voltage across the capacitor. We also use a spectrum analyzer connected to a standard antenna to estimate the RF power available at the Rectenna's input. In here you can see the wireless charging voltage of the capacitor, and you can see that at the distance of 1.2 meters, it only takes about 12 seconds to charge the capacitor to 1 volts. That generates about 3.5 millijoules of energy, which is more than enough to allow a low-power microcontroller to perform some sensing, computation, as well as transmit using a power-expensive protocol like Bluetooth, for example. Using the RF power we measured from using a spectrum analyzer, we can calculate the end-to-end efficiency. So we calculate the end-to-end efficiency as the DC power divided by the RF power available at the source, and this includes the losses in the antenna, the losses in the rectifier, as well as the losses, the internal discharge of the capacitor. And we have an end-to-end efficiency of over 15%. To put that in perspective, when the same supercapacitor was used with a mechanical ferroelectric energy harvester wall input, the end-to-end efficiency was significantly lower than 1%. So we really demonstrate that RF power and wireless power transfer is an efficient way of transferring power and charging a wearable energy storage device for Internet of Things applications. So to summarize my talk, we have presented a fully flexible textile-based power supply and energy storage, an entire system that can reliably power wearable electronics. Our energy generator, the RF energy harvesting Rectenna, can be easily integrated in textiles, is fabricated on a very reliable flexible circuit filament, and it's also very high efficiency, and it has more than 8 volts DC output from high enough 8 dBm power levels. For the entire system, the end-to-end efficiency, as I've just mentioned, is pretty high, over 15%, and this is the highest compared to other textile-based systems reported in literature. As for our future work, so it's more on the reliability. How much does this change when actually worn by the person? How does it change with bending? How does it affect with washing? And we also need to investigate the wireless charging over different separations for different transmitters and potentially for different antenna designs as well.